Nice. I like this. It's interesting. Yeah. I thought you use a big font. They write words in this font.
It's like.
Is it really? Yeah, I was just saying, you probably know this. Yeah.
It's a whiteboard marker. I don't know.
17 is like 35 pages, but it's like, it really went.
Okay, welcome back. Quick announcement, I said it before, but now we'll be more precise about it. Tomorrow is the first lab. It's an introduction to MATLAB. Variables, binding, simple operations, a little bit of plotting, things like that, getting used to the environment. Tuesday is also a lab. It'll start at the normal lecture time of 10, but it's also a lab, and it'll be kind of control structures, loops, conditionals, things like that. If you don't know what those words mean, then you should go. Or if you don't know MATLAB, you should go. Thursday will be a lecture, and then Friday will be another lab. So next week there will only be one lecture, 2 labs. Okay? And the real change is just that Tuesday is the lab. Okay?
Does
Question?
anyone doesn't have a MATLAB or don't know how to install it?
That's a good question.
No.
I believe there's instructions on
I put the
website
link,
now.
I'm pretty sure I put the link to the instructions for how to install MATLAB. If you have any trouble with that, you should let us know. But you
Yes,
probably
make sure
won't
you
want your
have
own
the-
copy on a laptop, or you can use any of the departmental machines that are available to starting students. Or come see us if you're having any issues with this. We can kind of make arrangements to get it installed somewhere where you can use it. Okay. Any questions from last time? Oh, let me say one other thing. After lots of attempts to put video online on YouTube, I'm still failing. I guess YouTube and I just don't get along so well. That's been true for a long time. So there's something on YouTube right now. I linked it from the web page just so you can have it, but the quality is pretty crummy. I don't know. I'm not sure what the issue is. I have to convert it into one format and then upload it, and then it gets converted again by YouTube and reduced. So the quality it's losing quality, so you can't really see the board. You can see it on the original video, so it's getting lost in the translational process. So I'm still searching for a way to do this, and our fallback plan is we will put it back on NYU Stream, where I know it's high enough quality you can see everything. That's what we did last year and the year before. So that's the fallback plan. We'll try to figure it out, hopefully by today or tomorrow. But there's a version of the video up now, and we'll put another one from today up in case anybody wants to look at it. Okay. Now, back to where I was. Any questions? Thoughts? Yeah?
Is the lab in this room?
The lab is in this room. I think tomorrow's lab is in this room, correct? You guys can verify that, but I'm pretty confident that's correct. And the lab starts at 9:30 tomorrow. Okay, and it'll go till like 11:40 or something, 11:45. Might stop earlier than that, but that would be the max. Okay. Some of you are taking, I think, the MRI course. I don't know how many of you, but there's a handful of you, and in order for you to get to that, we're going to stop a little before noon so that you have a little time to go grab some food and get to that course. Yes?
Is it just tomorrow that's starting at 9:30 or?
No, generally the labs start at 9:30. That's on that course information sheet. Did anybody not get a copy of that? Does anybody want a paper copy of that? Okay, nobody cares anymore. Paper. It's online in any case. On that sheet it says 9:30 for the labs, okay? And 10 o'clock for the class. And it's 5 after 10, so we're already late, which is also normal. Okay. So back to where we were. Last time we ended, but I didn't quite complete this, what I think of as really the core of a huge amount of stuff that we're going to do. Really everything that we're going to do in the next, I don't know, 5 weeks or something. Maybe 8 weeks, 7 weeks, something like that. So what am I talking about? The definition of a dot product is in terms of, as we talked about, right, multiplying pairwise the elements of 2 vectors and then adding up all those products. Okay? But in fact, that's one interpretation, and that interpretation is a description of how you might compute it, how you might write a piece of code, actually, if you were writing it out in MATLAB or in any other programming language, how you would actually do it, you'd write a little loop that would cycle through the elements, each index, and multiply pairwise and accumulate them in some storage place until you've added them all up, and that would be the answer. That's the dot product. But a much more, in many ways, a more useful way to think about the dot product is in terms of this geometric description I gave you. It's equivalent. An equivalent way to calculate a dot product is to take the length of the two vectors, so let me write it down. Okay, so I have two vectors, call them, and this is true for any two vectors, but they have to be, remember, the same dimensionality, same number of elements. The dot product of two vectors is actually equal to the length of the first, the length of the first vector times the length of the second vector. And last time, remember, I started out by pointing out that this dot product has to be proportional to each of these lengths, and you can kind of see that just from standard algebra and the definition. Right? If you multiply one of these by a scale factor, then the dot product will have to go up by the same scale factor. But in addition, there's one more piece, which we finished last time, which is the cosine of the angle. Well, the way I wrote it, I'll keep it consistent with what I wrote last time. I wrote theta x minus theta z. Right? It's just the, we don't have to write it as a difference, it's just the angle between the vectors. Okay? So there's an angle, the two vectors are pointing in different directions, there's an angle between them, the cosine of that angle enters into the dot product. Okay? And this is equivalent to the original definition, which looks completely different. Right? The original definition was this pairwise product and add them up. This doesn't look anything like that. This looks like take the two lengths and then take an angle. This is a more useful form to think about it, in which to think about it, because it gives you geometry. And so let's start with what geometry gives you. So under what conditions, oh, let me say one other thing before I do that. Notation for dot product. This is, often when we write it on the board, we're just going to do this. We're going to put a period there, but raised. Okay, so that's a dot product. You will also see, if you look in various pieces of literature, you will see, especially in physics, they often write this. Angle brackets with a comma between them. You will see sometimes people write, actually the way you'll see it often in MATLAB is really, this won't make complete sense to you yet, but it will hopefully by the end of today or the beginning of next time. You'll see people write things like this. Okay, so that is a product of two vectors where this one has a t in the exponent, and the t means transpose. You don't know what that means yet, but we will tell you shortly. There's no point in trying to explain it now. I'm just trying to give you a little bit of notation. So you'll see that expressed also. Sometimes in the homework we'll write it that way. And in fact, when you go to compute a dot product in MATLAB, you will often do it this way. In MATLAB, it's not a t, but it's an apostrophe. So in MATLAB, you would write, you don't have arrows over both of those symbols either. You would write x. If x is a vector, you would write x prime times, you use the asterisk for times, z in MATLAB. All of this will start to become clear as we go forward, and I'll explain what that transpose is. Okay? All right. Put that aside. Let's go back to what I was saying. Under what conditions can this thing be zero? And what does it mean if it's zero? Well, I'll start with the first question, and then we'll get to the second. Let's answer the first question. When can this thing be zero? Well, it's a product of three numbers, right?
Either the length of the one, which is 0, or the cosine.
Right, so any of these three things could be zero. If this is the zero vector, then this would be zero, so then the whole thing is zero, the product is zero. Right? And when is this thing zero? We talked about that last time. The only vector that has a length of 0 is the 0 vector, i.e. the vector that has all zeros for its elements, because if it had anything that was not a 0, that would contribute positively to the length, because all the elements get squared. So even if it has a negative element, it doesn't matter, it's going to get squared. So anything that's in there that's not 0 will contribute to the length. So the only thing that can possibly have a length of 0 is the 0 vector. So if this is a 0 vector, you get a 0. If this is the 0 vector, you get a 0. If neither of these is a 0 vector, you can still get a 0 if the cosine is 0. Then when is the cosine 0? For what angle? 90 degrees. Okay. So we now have We'll call this an orthogonality test. We can tell if we have two vectors and we take their dot product and we know they're not zero, a little check on the side. If they're reasonable vectors, they're not sitting in the black hole at the origin, then we can use this to tell if they're perpendicular, 90 degrees, right? That's the only way you can get a dot product of zero, if the two elements are not zero vectors, is if they're at 90 degrees away from each other. So that's pretty cool. We have a very easy way to test the geometry of orthogonality. And we can do that actually not just in 2 dimensions, but in 100 dimensions or 1,000,000 dimensions. If I give you a 10 million dimensional vector and another 10 million dimensional vector, they point off in this space that we can't visualize. But I can tell if they're orthogonal to each other by just taking the dot product and looking at the number that comes out. If we can do it in 3 dimensions too, any number of dimensions. Okay? So this is very, very powerful. It allows you to reason about the geometry in any dimensional space. It's completely general. Without having to do some complicated calculation with trigonometry or anything. You just take a dot product, which is just adding the products of all the paired elements, right? So it's easy to calculate, and yet it tells you this geometric thing about your vectors. Okay. You might also ask, well, how do I know if two vectors are parallel, like pointing in the same direction? That one's maybe slightly more complicated, but you can also use this to figure that out. So if they're in the same direction, that means the angle between them is 0. What's the cosine of 0? 1. Okay, so in the case that you take a dot product and what comes out is just the product of the two lengths, and this is 1, then it must mean that those two vectors are pointing in the same direction. Right? What if it comes out negative, the product of the two lengths? So I have two vectors, and I take their dot product, and what comes out is the length of one times the length of the other, but it's negative. What does that mean? It means that the angle must be, the cosine is -1, because these things have to be positive. The cosine must be -1, that's where the negative is coming from. And if the cosine is -1, the angle must be 180. So they're pointing in opposite directions if it comes out equal to their product of their lengths, but it's negative. Okay? Which sort of means they point in the same direction. They're lying on the same line, is the way we described it last time. Okay? All right. So that's it for the geometry. Now, let's do something else. Yeah.
Did you want to say anything about the fact that it still works beyond 3D?
Well, I just said it, but you will have to say why.
You proved it for 2. I don't know if that's
I don't think we're going to go there, because there's not an easy way to do it. We're going to wave our hands, sprinkle a little magic. Okay. Let's, so, a dot product is a symmetric operation. This x dot z is equal to z dot x. And how do I know that? If I wasn't sure of that, how would I verify it? How would I prove that that must be true? Any idea? Well, you have two formulas for the dot product now. 2 ways to think about computing it, right? So you have the one that's on the board. So this thing is a product of this length and the difference, the cosine of the difference of their angles. If I switch the order, x and z, what happens? Well, the product switches, but that doesn't matter. The product of a and b is the same as the product of b and a. Multiplication, plain old scalar multiplication, it's commutative. And then the last thing is that this thing is a cosine of an angle, and if I switch the order of this, the angle will be negated, right? Instead of theta x minus theta z, it will be theta z minus theta x. But that isn't going to matter because the cosine is an even symmetric function. I also said that last time. Okay? So switching the order of x and z makes no difference. You can also see this just by looking at the original definition that I gave you, right? Which was, if you remember, a sum over the indices of x sub n times z sub n. And it's obvious from that description that if I switch the order of the two things, x and z, it won't make any difference because then it's just the same sum, but now it's zn times xn. But of course, zn times xn is equal to xn times zn because that's the scalar thing that you know, again, since grade school. So a lot of the properties of this are inherited from plain old multiplication. It is a form of multiplication, but it's kind of a special one because it operates in multidimensional spaces. It operates on vectors. All right? Okay. So, back to this point. So the operation is symmetric. X and z, doesn't matter which one comes first. And we usually, if we want to think about the math of dot products, it has this complete symmetry. It's invariant to swapping them back and forth, and it doesn't matter which one is which. Often, when we use dot products, and we're applying them to some problem, either a math problem that we're trying to solve, or we're applying them in an engineering system, we're trying to compute a dot product, or we're thinking about them as a model for some piece of biology, which we're going to do in about a week and a half. They're not going to be symmetric. We're going to have identities of the two things in the dot product, where one of them is kind of an input vector. Think of, let's say, x as being the input vector, something that's coming into a system. So if you need a concrete example, imagine the light coming in your eye and landing on your photoreceptors, and you're measuring with a discrete set of photoreceptors the amount of light landing at each location in the back of your eye. So that's a vector. And you can think of the intensity of light as the vector of numbers that describe the light that's going to land on each photoreceptor. And then each photoreceptor has a response, and maybe the photoreceptors are different, so they respond differently to the light, and they each are going to weight the amount, their response, right? Each of those responses is going to get weighted by a number, and those are the z's. So this is a situation where the x and the z are not the same. They're the same mathematically, but they're different in terms of our interpretation and the way we use them to set up the problem. And one of them is really sort of data or input. It's a signal. And the other one is what I'm going to call an operator. It's like operating on the data. It's weighting the data in a particular way and then adding it up. So this would be a very simple description of an operation you might perform, which is a weighted average or a weighted sum over the pixel intensities. And we're going to look at that in just a second right now. So let's just go through a few examples so you know what I'm talking about. Because we're going to see a lot of this as we go through the semester. And you're going to find in this course that we often kind of flip back and forth between thinking about the math, like what's written on the board there, and then thinking about, oh, well, what if I wanted to use this math in some context of thinking about some system? I'm trying to describe a perceptual phenomenon, or I'm trying to describe something about the interaction between two populations of neurons, or I'm trying to describe some calculation that I want to do on MRI voxels in order to extract some information about what the brain is doing during a task. I'm going to think about the data as one vector, and the thing I'm doing to the data as maybe another vector, an operator. Okay. So how do I do this? What's the simplest example? Let's say I want to compute the average. So I have a bunch of data. It's in a vector, a bunch of numbers that I measured. Let's say there are, it doesn't matter, let's say 4 of them. And I want to compute the average of those 4. And normally, you would not need to use linear algebra to do this. You would just say, well, give me the 4 numbers, and I'll add them up and divide by 4. It's pretty straightforward. You've been doing that for a long time. Linear algebra gives you a compact way to write that, and it's going to allow us to do more than just that simple average. So how do you compute the simple average? Let's start with that. So I need an operator. And I want to know what operator should I use. So I have my input data, x. And it has, I'm going to draw it as a spike plot. It's got 4 numbers, and I want to compute the average of those 4 numbers. What do I do? Can I do that with a dot product? That's what the dot product looks like. Here's my input vector. I want to compute the average of those 4 numbers. How do I do it? Writing it as a dot product. No. Am I asking it in a strange way, or nobody wants to venture a guess? Nobody wants to be wrong. One of my favorite quotes is, all models are wrong. All answers are wrong. Everything we do is wrong. It's okay to be wrong.
Your z vector could be a vector of 1s, and then you have a scalar of n, or 1 over n.
1 over n, and here n is 4. So if I don't have a way to indicate because I didn't draw a scale, but I'll just write 1/4 over here. The idea is that these things are each 1/4, so this is kind of a dome vector. It's a vector has all the same element. Every element is the same. In this case, they're a quarter, because I want them to be 1 over the length of the vector. And now when I take a dot product of this and this, what do I get? I get a quarter of that, a quarter of that, a quarter of that, a quarter of that. Add them up. That's the average. So this thing, operating on that thing, computes the average of those values. If this was data, a bunch of measurements that I made, I want to compute the average, I just have to take a dot product. And I don't have to write out all that summing and dividing, I just have to generate this vector and then take the dot product. Okay? So that's it. And we can think of this thing as an averager. If I think of, again, x and z are not distinguished in terms of writing the equation for dot products, but now I'm thinking of this one as an operator that will operate on this one, which is the data, or the input, if you like. Okay, so that's easy. What if I wanted, I'll call it a windowed averager. What if I want the average of the middle 2 elements of x, but I don't want the others?
Leave the first and last 0.
Right, so I can leave the first and last 0, and there's one other correction, right? So I'll put a little dot here just to indicate there's a 0 here and here. And I have these two, are these 1 quarter? No, I have to make them 1/2 now, right? So in some sense, what I need is to sort of multiply by something that's ones, and then divide by the number of ones that are in here, if I wanted to act like an average, right? So I would need to think about how to calculate that. Actually, how do I count the number of ones that are in here? Let's say I have a vector that's all 1s and 0s. There's 1, 1, 0, 0. They don't have to be next to each other. 0, 0, 1. Okay? Now this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so it's 9 elements long. 10 is 9. And there are 4 1s in there, and the rest of them are zeros. How do I count how many 1s there are? And of course, one answer is I just tick my way along the list and ask, is it a 1 or a 0, and add up all the 1s. But how do I do it with the dot product? Again, you have to think of computing, making something that will operate, that is an operator, that will operate on this thing and hand back an answer, which is the number of 1s.
Another vector of functions.
Right. It's pretty simple. A vector of all 1s will, when you multiply 1 by 0, you get 0. When you multiply 1 by 1, you get 1. And when you add all of those up, you'll get the number of 1s. So if I multiply any vector, a binary vector, by a vector of 1s, I get back the number of 1s that are in the vector. Okay, so now I know how to compute in general an average, a weighted average. How do I compute a general weighted average? Let's say that I make my weighting function, z, and it's got 2 1s in it now. They're not supposed to be 1s, they're supposed to be half, because I want to compute the average of those 2 elements. These are 1s. That's not going to give me the average. So what do I really want? I want to compute this. I want to do x dotted with z, and then I have to divide by the number of 1s in z, which is just, I'll write 1 dotted with z. What's 1? This is a vector of 1s. So if I compute the vector of 1s and dot it with z, I'll get the number of 1s that are in z. And then here, I take the elements that have the 1s out of x, and I add them up, and I divide it by the number of those elements, the number of 1s, and that's the average of those elements. So now I wrote a very general formula for computing the average of any subset of elements out of x. What do? I make a z, that's my operator. I choose values, I put 1s in the locations of z that I want to include in my average, and then I just calculate this thing. And this is automatically doing the normalization that I need to calculate how many things am I averaging together, right? And it's again a dot product. Okay. And you can think about really, you can factor this. This is a number down here. So the right way to write this would be something like, if I want to write it as an operator, so this is just going to kill us this semester. Okay, let's write it that way. I just factored it, okay? So this is a number. instead of dividing by the number at the end, I can instead divide z by this number. Right? Doesn't matter, it passes through. I can either put it on the z, or I can do it after I've done the dot product with the numerator. If I factor it by dividing z by this number, that's what I did here, then this thing, I'll put blue around it, that's my averager. And x is my input. So the operator is the z, it's filled with ones, wherever I want to include, whatever I want to include in the average. And then this thing, which tells me the number of ones. Okay, everybody following? All right. So that's an averager, or a windowed averager. I called it a windowed averager. It's even more general than that. A windowed averager, what do they mean by windowed? I mean, like you cut out a window out of the middle of your vector. In this case, it was the middle 2 elements. If this was 1,000 long, we could say pick out the middle 50 elements, right? It doesn't matter which window I'm chopping out. But I already showed you with that example of the z that I drew over here, that there's nothing that says those have to be next to each other. I can pick any elements I want. Put a 1 here, put a 1 over here, put a 1 all the way down at the end, it's fine. Take the average of the first and the last element, that's fine too. They're not next to each other. They don't have to be contiguous. They can be any subset I want. In fact, it's even more general than that. A Gaussian averager, that's another example. So there's nothing that says these have to be zeros and ones. I can pick, you know, let's do half of this one, 1 of this one, 1 of this one. The same formula is going to work. This is just add up with these weights, half of this, all of this, and half of that. So it's now a weighted average, where I've weighted things by this vector. And I still, if I want it to be an average, I still have to make sure that the weights add up to 1. And how do I calculate the sum of the weights? Again, by taking a dot product of z with the vector of 1s. What does that do? When I take a dot product of the vector of 1s, it adds up all the elements. Each one multiplied by 1. So it's the same formula. This thing can compute a weighted average. It doesn't have to be zeros and ones. And in fact, if I had a big long vector with lots and lots of elements, not just 4 as I've drawn here, I could imagine doing some nice smooth function. Now we're getting toward, sampling some smooth function. So let's say that I have, what I really want, I have a big long signal, it's 1,000 elements. And what I really want is an average of the ones that are in the middle weighted by something that looks like a Gaussian, a normal distribution curve, right? And the weights, I'm saying these are very dense samples. I want to take weighted, so now I'm going to take an input vector that's however long that is. Let's say it's 100. 100 samples long, and I'm going to take a weighted average of all those samples weighted by these numbers. The formula is the same. I stick in these numbers, whatever they are. They have this shape. And then I have to normalize it. I have to divide by the sum of all these numbers to compute a weighted average. And the sum of all these numbers is again computed by taking a dot product of z with a vector of 1s. So once again, I can compute an average with this weighting just by starting with this shape and then doing this calculation. Okay? Everybody good with this? All right. So far, basically this tells you how to compute something you already knew how to compute. We will eventually get to things that you don't know how to compute, and that's when the power of this will really emerge. You start with things that are sort of simple and concrete that you already know about, and then you show that this actually gives you a way to generalize those ideas. All right, the differencer. So now, averages are usually adding things up weighted with positive weights. But sometimes there's nothing that says z has to have all positive weights. It's allowed to have negative weights. And the simplest example of something that you might want to do that has negative weights, an operation that you might want to do, and we'll see a lot of this, is a difference. So if my elements look like this, I might want to do something which is this thing minus that thing. Okay? Why would I want to compute a difference like that? all know calculus. Where in calculus do you see something where, let's say I have an input, here's x, this is z. X is, I don't know, x is something like this, and I'm thinking of it as samples of some sort of function. And I'm now saying I want to operate on this by computing the difference between two adjacent values. Why would you do that? Pardon? Local extrema. Okay. You could use this to look for extrema. Like you could look for a place where the difference is small, or when would the difference be really small? Like if you had two adjacent points that were the same. And the function, this wiggling line that I'm drawing, if they're the same, it's like the function is flat in that location. So what am I, when I say the function is flat, I'm not talking about the slope of the function, right? So what do you do in calculus to measure the slope of a function? Compute the derivative, right? Okay, and how do you, what is a derivative in calculus? Anybody remember where it comes, how you define the derivative in calculus? Take the difference between two adjacent values of a function. But you don't stop there, you have to do something else. You have to, okay, you divide by the spacing between those, where you took the two measurements. Okay, so you measure two values of the function next to each other, and you take that difference in values, and you divide that by the difference in position, basically, the delta between them. But then you take a limit, right? You let that delta get really, really small, because you don't really want like a discrete difference. What you want is in the limit, as they're right next to each other, what's the function doing? Is it going up? Is it going down? Okay, so you take the limit. If you have something that's sampled like this, a vector, that only has values at these locations, you don't have that continuous function, you only have these values, then you might have to make do with a discrete approximation of a derivative. So a difference is the simplest way to approximate a derivative. You just take the difference between two adjacent points, and you can't, and you assume the spacing between them, you call that one unit. And so this does compute a derivative in a sense. It's not really a derivative because you're not going to take the limit. You can't take the limit because you only have the values of these locations. But this is something that will come up when we get to, a little bit, when we get to convolution and Fourier transforms. But already we kind of see that this idea is something that's going to allow us to compute things on discrete signals, like for example the music that's recorded on a CD or digitally streaming from Spotify. Those samples, if we wanted to compute derivatives of what that music sound wave is doing, a pressure wave, we would do something like this. We could compute that with a dot product, taking a derivative, an approximation of a derivative. Okay, so we think of that operator as a local differencer. And, okay, here's, and I guess I probably should have started with this one, the simplest operator of all. What if I just want the nth element out of x? X is a vector, it has elements that are indexed starting at 1. What if I want the fifth element? How do I pull that out? Right, so it's kind of a trivial operator, really. It's, you know, there's one, right? This doesn't pull the fifth, this pulls the fourth element, right? So 0, 0, 0, 1, 0, 0, 0, 0. There's a 1 here. If you take a dot product of this thing with this thing, what do you get? Everything gets multiplied by 0 except for that element. So this is a selector. It pulls out one component of this vector and hands it back. And depending on where you put this 1, that's the element you get back. In fact, you could make a whole family of these, one for each location, and each one of those would pull out a different element. It's kind of trivial, right? It's not doing anything. It's just handing you back the elements of the vector, but you already have the vector, so you know what the elements are, so it seems a little bit silly. But it comes up, these come up a lot, it turns out, because this is, in a sense, the way this vector is represented. It is represented in terms of these things, and we're going to see that, I think, on the next slide. No, not quite. We have something else to do first. We'll come back to it. All right. So, now that we've done that, let's do the next thing that we have to do. We're going to use the geometry. We started using the geometry of the dot product. We started using that to give a little test for orthogonality or parallel vectors, right? Two vectors are orthogonal if they're both not zero and their dot product is zero. I just use the word orthogonal instead of perpendicular, but I mean the same thing. I mean they have a 90-degree angle between them. Okay? And they're parallel if their dot product is equal to the product of their lengths. Okay, now we're going to do something more general. So, I'm going to redraw what's on the board, or on the slide. And I'm going to draw it a little bit bigger, I hope. And we'll work through this piece by piece. Okay. What I want to think about is the following. I'm going to assume I have one vector that's a unit vector. Remember, a unit vector is a vector with length 1. So I'm going to take a dot product of two vectors, but I'm going to assume that one of them is a unit vector. And what do they use in the slide? V and U, okay. So I'm going to do, let's write it as U hat dot V, okay? Where this one has a hat over it because it's a vector, but I'm trying to remind us both with the letter U and with the hat that this is a unit vector at length 1. And so, of course, the dot product, we already wrote this, I just erased it in the general form, but for this case, it's the length of the two vectors, product of the lengths of the two vectors and the cosine of the angle between them, but one of them has length 1. So this is just the length of V. The length of U goes away because it's just a 1, and then the cosine of the angle. And now I'm going to write something a little different. I'll write just theta UV. Or maybe just to save the notation, we'll write theta by itself. And you know that I mean theta is the angle between the two vectors. We'll draw it in a moment. Okay. So let's do this. So here's U. Ooh. U hat is this. Okay? And V, I guess we'll do V in green. There's V. And now we want to think about the geometry of this thing. Okay. This thing says take the length of V, so whatever the length of that green line is, and multiply it by the cosine of the angle. And the angle we're talking about is this angle. This is theta. So geometrically, I want to draw a triangle that's going to help me interpret what that means. It's this thing times the cosine of the angle. Cosine of the angle is it's the adjacent divided by the hypotenuse when you're thinking about a right triangle. So I can draw a right triangle in here. It's this one.
Can we nip it on the slide?
It's on the slide. That's correct. I can draw a perpendicular right here. And when I draw that triangle, now I can think about that equation. I have this thing, which is the hypotenuse, times the cosine of this angle. So what is that? This thing times the cosine. Well, the cosine was the adjacent part, which is this thing. Let me draw that more clearly. This is the part that's hard to see on the slide or understand on the slide. The length of this, from here out to this perpendicular, is the adjacent part of this triangle. Cosine of theta is that adjacent part divided by the length of V. So if I take that thing, divided by this thing, I get the cosine of theta. If I take the cosine of theta and I multiply it by the length of V, which is what's written up there for the dot product, all I did is just take it from one side of the equation, put it on the other side. That thing is equal to this. So the length of this thing is exactly U hat dot V. The length of this thing, this vector. It's the piece, if I take V and let's think about it this way. This unit vector is just a way of representing a line. It's the way you should be thinking about this. The unit vector specifies a line. It says there's this line through the origin and it goes in this direction. This thing is saying, if I ask how much of V lies along that line, what piece of V lies along that line, I can measure that, and I can calculate how big that piece is just by taking the dot product. Again, the dot product is that zipper picture, right? It's just multiplying the paired elements and adding them up. So it's not obvious that that would be true, but it comes from this more geometric, trigonometric equation that allows us to think about the geometry. So the geometry is that the length of that thing is equal to the portion of v that lies along this line. And if I wanted to express the vector, this vector that lies from here and ends here, so this thing is a number, it's not a vector. It's the length of that vector. How do I write the vector itself? And that is on the slide. It's easy. I take a unit vector in this direction and I multiply it by that length, right? I already have a unit vector in that direction. That's u hat. Right? So I just take this thing, which is a number, and I multiply it by u hat, and I get back the actual vector. So this thing times u hat is the actual vector from here to here. Okay? And that's what's on the slide there. So this thing, this vector, the one that is in the direction of u hat, but extends out to here, is just u hat multiplied by that number. Okay? So, and we call that a projection. Okay? So that vector is the projection of v onto the line defined by u. It's the piece of v that if I wanted to write v in terms of a piece that lies along u, I would write that. And now there's another piece. That's not v, that's just the piece of v that lies along u. If I wanted to complete this and describe, well, what's left, there's another piece. You can sort of see that if I take this thing and I want to get back v, what I would need to do is add this. I have to go from here and I have to add that. Adding two vectors is putting them head to tail, right? So what I really need, if I want to get back to v, is I need to take this thing, which I've just defined here, and I need to add this piece. So what is that piece? Well, let's see. That thing is perpendicular to u hat, and it's pointing in this direction. It's kind of like the piece of v that you would get if you were to project onto this axis, right? So if you took v and you dropped a perpendicular this way, I just made a rectangle, right? You drop a perpendicular this way, this vector is the piece of v that lies not along u. It's what's left after you remove the piece that lies along u. In fact, you can define it that way. You can write that this vector over here is v minus that piece, u dot v, sorry, u hat dot v. I got my hat in the wrong place, times u hat, right? Okay, so this, v minus this, is this piece. And this, add these two things together and you get v. Notice that what we just did, it's kind of interesting. What we just did is we took v and we described it. V is originally described in the coordinate system that's on the board, the horizontal and vertical coordinates, right? V is it's two numbers. So I'm drawing everything on a plane here. V is two numbers. It's a horizontal and vertical coordinate. And we could draw a dashed line from v down to this axis and say, well, that's the piece that lies along the horizontal direction. And I could draw a dashed line horizontal over here and say, well, that's the piece that lies vertically. And v is really expressed as a sum of two things, something that's horizontal and something that's vertical. So what did we just do now? I just rotated everything. And I said, well, actually, I can describe v didn't have to be described in terms of the original coordinate system, this thing and this thing along these axes. Now I'm describing v in terms of a new coordinate system. I'm describing the portion of v that lies along this axis. It's a different axis. It's not the horizontal one. It's some other thing defined by u hat, and u hat is whatever I decided it should be. It could point in any direction. Right? There's nothing special about the one that I chose when I drew this. It's kind of random. So I can now define v in terms of a new set of coordinates. There's a coordinate along this axis. What's the coordinate? What's the number that I have to use to describe it along this axis? Well, that's just this dot product, right? If I wanted to describe it in terms of a vector, then I have to take that dot product and multiply it by this unit vector, and that gives me this piece, right? And then there's another piece, which is this piece, which is orthogonal to this piece. So it's exactly the same as the description of the original coordinate system. It's just like a rotated coordinate system. That's exactly what I did. I rotated the coordinate system from the original coordinate system and now in a new coordinate system. So dot products with unit vectors allow us to calculate things that are in different coordinate systems. So that's the last point here. And now we have to do the middle point. So we're going to see a fair amount of this from starting, I think, next time. This idea of rotating coordinate systems and how to do that and how to work with calculations that rotate coordinate systems. And this is the beginning of it. It all comes out of the simple geometry of a dot product with a unit vector. Okay? And that is given to you by that equation with the cosine in it. It allows you to think about what the geometry is and what this means. Again, I should point out that this is going to be true in multiple dimensions. So if you had pointed out in some other direction, I can still do this, I can still ask this question, how do I represent, what is the piece of V that lies along that direction? So if this was a three-dimensional vector, I would, and my V was in the board and U hat came out here, I can still take that line that is defined by U hat, and I can drop V onto that line perpendicular, and I can measure that distance, and that distance is again just the dot product. And if I want to make that vector, I can again take that length and multiply it by U hat and get back that component. The difference is that now in 3 dimensions, I would not be able to describe everything in terms of just 2 vectors. I'm going to need 3. You need 3 axes to describe something in 3 dimensions. You need two axes to describe something in 2 dimensions. So here, when I rotated this coordinate system, I have 2 axes. There's this one, and then there's the one that's left over in the perpendicular direction. If I do it in 3D, then I have to describe 3 axes. Okay? So we're going to get to that, but I'm giving you a little bit of a heads up. All right, so that's a little bit about coordinate systems, and now let's look at something else that we can do with this, which is going to turn out to be useful, and it's going to be the basis for regression and optimization. We already hinted at this last time, and now we get to see a little bit more of it. So what is that? What if I want to measure, the distance. Let's see, make sure that I'm doing this the way I want to do it. Something that will come up is repeatedly, and we're going to start by looking at it right now, but we'll see it again and again and again over the next few weeks, is the following. We're going to ask the following question. If I start from V and I ask, what point along this line defined by U hat, where is the point that is closest to V? So I can consider lots of points along this line. Let's draw a couple of them. Here's a point, 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 here's a point. Okay, so there's a bunch of points along this line. And I can think about what's the distance of each of these points to V. And as I move along here, I can think about, well, what's happening to the distance? And I'm over here and I'm moving this way, the distance is getting smaller, I'm getting closer to V. Closer, 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 closer. And at some point, I'd start getting farther away, right? So there's a sort of point that is closest. If I wanted to think about the optimization problem, how do I find the point along here that's closest to V? If you need a physical image of this, imagine that this is some sort of a long stick. And there's a nail in the board here, and I have a rubber band that's tied around the nail and also looped around the stick, and I let go of it, and there's no friction. So the rubber band can go anywhere it wants, but it wants to be as short as possible. It's looking for the position where it can sit, that it will be as close as possible to be, because it's a rubber band, it's under tension, it wants to be shorter. Where does it end? Where does it settle? And the answer you probably know intuitively. There's a point of symmetry where if you go any further, it starts to get further away from V, and that point is basically the place where you drop a perpendicular onto this line. Right? That's the closest distance. I erased it, and now I'm putting it back. The perpendicular line gives you a point which is closest to V. If you go a little bit away from that, you're further away. And the reason is pretty simple. This is a right triangle, and the hypotenuse of this triangle will always be longer than the adjacent side, or at least as long as. And so if I go out here to bigger and bigger angles, then I'm basically adding, Pythagorean theorem. The hypotenuse is the sum of squares of the distance, this perpendicular distance to this line, plus, that's the square of this, plus the squared distance along the line from here. And so any place I go over here is going to get bigger. The hypotenuse is getting longer and longer and longer. And the same thing is true as if I go this way. And the best I can possibly do is to stop right here at this perpendicular point. So this projection that we were talking about, this thing, V minus, well, let me write it down. U hat divided with V times U hat. That's the closest we're going to get to V. And if we ask, well, what is the distance from V to this? It's just taking this vector, the V minus this, and taking the length of that vector, which is kind of a very messy expression. So very quickly, these things start to look ugly when you write out lots and lots of vectors and with dot products. But in fact, these calculations are things that can be done very easily using linear algebra. And this is the beginning of our foray into essentially regression and optimization. We're going to see this kind of thing again and again, and it's actually going to get simpler. It's a little bit harder when we're still in this case where we're drawing triangles and trying to think about dot products. It's going to get simpler, but this is really the root of it. This is where it comes from. When you want to minimize distances between, in this case, I was talking about a single vector, but imagine I had a whole cloud of points, many vectors, and I want to find a line or a plane that goes through those vectors and minimizes the distances of all those vectors perpendicular to the line. Those distances are expressed like this. And when we go to minimize them, we'll be able to write down a fairly simple equation that expresses how you go about doing that in any number of dimensions, with any number of points, and with any dimensional thing that you're trying to fit, a line, a plane, a hyperplane. Okay, so that's where that is going to come. It's all going to come back to understanding this piece of geometry, which is why I'm belaboring it a little bit. Okay. Do I have anything else I want to tell you? The distance to the line, distance along the line, projection, and I already told you about the coordinate systems. Okay. So now, I'm going to switch back to the previous mode of thinking. We were thinking about operators, right, on the previous slide. I told you that you can think a dot product was a symmetric operation. But we can think about one of the vectors as being an operator and the other one as being some sort of input. We're going to switch back to that mindset, and I'm going to try to express for you so linear algebra kind of comes into the analysis and processing and the modeling of data in two different ways. One is just as a tool for doing calculations, like regression. But the other is for building models, for actually building simple models or building parts of models. And when you're building models, you're thinking about it more in this context, okay? So we're switching back to the model framework. The idea now is I have a system. Think of the operator I told you about on the previous slide. The system is a box. It's a big box that takes an input. The input is a vector. And the system operates on the vector And when it's all done, it puts out another vector, the output. So this is a box that takes an input as a vector and has an output that is a vector. Think about your ear. We can think about the sound that comes into your ear over time as a vector if we sample it. And in fact, all digital audio is done that way, as I've already described. So there's a vector coming in, and what is coming out are actual responses on your auditory nerve. Let's just call them firing rates so that we can keep it simple. Let's call them numbers, which represent firing rates on your auditory nerve. And your auditory nerve has a couple thousand neurons. So you have an input vector, which is some chunk of measurements of sound pressure over time, and you have an output vector, which is the response of those auditory nerve fibers also over time. So you have a vector in and a vector out, and in between is some transformation, because it's not just copying the input and sticking it on the output, it's doing something to it. So when we think about system, we think about transformations, and the simplest transformation, and really the one that we understand best how to analyze and how to work with, is a linear transformation. So a system that performs a linear transformation, we call that a linear system. And the definition of a linear system is what's on this slide. So a system is called a linear system if and only if it obeys what's called the principle of superposition. People often teach this sort of divided into two components, but I'm kind of smashing it all together here. So let's just look at the diagram, and then we'll go back to the equation. So the diagram goes like this. If this thing is equal to this thing for all inputs x and for all scale factors a and b, then the system is linear. That's a definition of a linear system. It's a math definition. Okay, so what is this thing? S is my system. If I take two inputs, x and y, they're vectors, and I scale them by factors a and b and add them together and stick them into the system, it must be the case that the response is exactly the same as what I would get if I instead put x and y into the system individually, x and y, and then rescaled them at the other end and added them together. Okay? So what you're really saying here is that S can be commuted, it can be switched. The order of operations here can be switched. I can take the S, instead of doing it at the end, I can push it back through the system and do it at the beginning, and it doesn't make any difference. The same answer comes out. So S can be permuted with these operations of multiplying by scalars and adding things together. That's the principle of superposition. Sometimes people prefer, again, I said this before, but you can break this down into two simple properties that are maybe easier to express. One of them is, just look at half the diagram. If I take an input and I rescale it, multiply it by 2, and put it through a linear system, it has to be the case that that's the same as taking the original input, putting it through the linear system, and then multiplying it by 2 afterward, right? So rescaling something at the input is the same as waiting and just rescaling it at the output. You get the same answer. It doesn't matter whether you put the scale factor before or after. Okay? But that's called, what's the word for that? Homogeneity. So, and then the other piece is that if I add two things together, let A and B equal 1. Okay? In that case, x plus y going into the system is the same as running x through the system, running s through the system, y through the system, and then adding them afterward. Okay? So we can break it into those two pieces. One is that you can rescale things, and it doesn't matter whether you rescale before or after. And the other is you can add things, and it doesn't matter whether you add them before or after. Okay, so that's the definition of a linear system. And that has to be, this has to hold for every possible x and y input vectors, and every possible a and b scale factors. And if that's true, then the system is linear. So it's a real mathematician's definition. And it's actually, in some sense, it's terrible from the perspective of a scientist. Why? What do I mean by that? Get you guys to think about the differences between math and science, or engineering and math and science. I think of those as three different endeavors. They share a lot of common language and thinking, but they're really different. They have different goals, and they have different ways of reasoning about things. So this is math. Math, I just state the definition. I'm allowed to say for all possible x and y, and for all possible a and b. But if I switch my mindset and I say, well, I'm a scientist, And I'm not defining a system to be linear. I have a system like a brain, or I think I have one. At least most mornings I have one. Some mornings it's a little off.
It's on coffee.
It depends on coffee, exactly. But I had 3 doubles this morning, so I'm all right. Waiting for that third one to kick in. So the critical thing is that if you're thinking as a scientist, your S is something in the real world, and you're making measurements, doing experiments. And so what you get to do is not just assert that the thing is linear. What you're trying to do is test, is it linear? So how do you test? Well, the definition suggests that what you have to do is try pairs of x's and y's and choose different a's and b's and do this thing. And then you have to go and do this thing. You have to take your system. So let's say that let's be concrete. I have a human in an MRI scanner, and I'm showing stimuli. They can be visual or auditory, doesn't matter. With whatever stimuli you want. Pain stimuli, I don't know, emotional stimuli, something, doesn't matter. What I have to do is I have to pick a bunch of stimuli, and I have to look at how some voxels light up. Could be 1 voxel, could be 100 voxels, could be all the voxels in the brain. That's my output vector. And I'm going to put my inputs in, and I'm going to try different inputs scaled by different amounts and look at the voxels that come out. And I'm going to also have to take those individual inputs and run them through and look at the voxels that come out. And I want to verify that if I take the voxels from the individual inputs and I do this calculation, that it looks the same as if I were to add the inputs in this way beforehand. So I have to make measurements, and I have to make measurements over lots of x's and y's and lots of a's and b's. I have to make lots of stimuli, if you like, and I have to test and make measurements. So why is that problematic? Why is this definition going to be problematic for the scientist that is hoping to assert with confidence that the system is linear? There's a bunch of answers here. Anybody see a problem with this?
It's hard to get all possible stimuli.
Yeah, it's not just hard. but that was, I appreciate the attempt to not stick your neck out too far. That's fine. You can't do this. You can't do this, right? You can't, because literally, if you're a mathematician, this means for all possible vectors and all possible a's and b's, right? That's a lot of measurements. Like that's your whole lifetime, and you're still not done. So you can't do it. It's not possible. You can make a large number of measurements. Lots of people in communities across the world can make lots of measurements. We can pool all those together in our scientific efforts, and we can say, you know what, it's looking pretty darn linear, but you still won't be sure. Because it only takes one failure to falsify the whole thing, right? So what if you know, the devil is in the box, and the devil, or if you want to go back to physics, Maxwell's demon is in the box. Right? So some of you that have taken physics maybe heard about Maxwell's demon. So Maxwell's sort of talked about boxes of gas, and why can't you take 2 boxes of gas and open a little hole, and imagine there's a little demon there that every time a gas molecule is coming toward the hole, opens up the hole and lets it through, but if it's coming the other way, closes it and doesn't let it through. Eventually you could put all the gas molecules on one side. So but you can't actually do that because the demon would have to have this incredible knowledge of where every particle was and how it was moving, etc. So this becomes a thought experiment for physics and thinking about thermodynamics and entropy and information. Here in our context, if there's a demon in the box and the demon says, you know what, I'm going to let the humans, the scientists, I'm going to let them think that this is linear. Every time you come up with a stimulus, I'm going to pass it through, and it's perfectly linear. But there's a few special stimuli that I'm going to do something crazy with, very nonlinear. And I'm not going to tell you what they are. You'll never find them, right? It's a needle in a haystack problem. You'll never find them because all the possible stimuli you try, you'll just never happen to land on the one that's going to mess up and show you that this is not linear. Another way of saying this is, in science, you look for falsifying theories. Right? You have some hypothesis that this thing is linear. You're going to look for failures of that. But you can't, but no matter how many successes you observe, you're never going to be able to assert with full confidence the way a mathematician would that the thing is linear, i.e. it obeys this. Okay. You can't make all the measurements. The other reason that this is difficult is not only can you not make all the measurements, but real systems are noisy. A measurement is not a precise, exact thing. And when you repeat a measurement multiple times, no matter what field you're in, any scientific measurement, it's going to come out a little different each time you make a measurement. So even that is telling you that something is going to be difficult to assert here, and you're going to have to bring in things like statistics, and you're going to have to think about, well, how close does it have to be for me to assert that it's linear? So that's another thing that's going to get in the way, in addition to the fact that you can't measure all possible inputs. Okay. So that's just a little philosophy and a little bit of commentary on how math relates to science. So this is an idealization. Real systems are actually, what we can do is notice that in fact, even if you could make all the measurements, you can realize in advance before you made the measurements that no real system is linear. No real system can be fully obeying all of this. Because what happens in a real system that takes real signals and has to operate under real constraints, energy and response levels, that's of course true of the brain, but it's true for all other real physical systems, is that if you amp up your input enough, eventually you're going to destroy the system. So think of your visual system and think of asking whether it's linear with respect to light. Obviously, if I make the light so bright it's like brighter than the sun, and you're staring at it and I'm trying to make this measurement to assert whether you're linear or not, that's the last measurement I'll make. And that's the end of the experiment. And now, okay, we can't finish figuring out whether you're linear. I don't ever get to test the superposition because once I've blinded you, it's done. So you're not linear, obviously. And no biological system is truly linear, and no real physical system is truly linear. Despite that, all models are wrong. I told you that already. Any linear model is going to be wrong for sure. Still, it is useful. So this is the full quote is from a guy named George Box. He was a statistician. And the quote is, all models are wrong, but some models are useful. Linear models are useful because they come with all these tools that allow us to think about and reason about them. And we can actually compare different linear systems. We can ask about their properties. We can very quickly determine and analyze what they do. So these are extremely useful models, even though they're wrong. All right. So, Mike is nagging me for a break. How many of you would like a break? Okay. Great. Pause the video. We just had a query about how many of you are sitting frustrated that it's hard to write on your lap? Quite a few of you. Okay, so we can't move tables in here. We have fold-out tables. They're in that closet, but they will not fit in here with all of these people. So I'm thinking maybe we'll look into asking whether we can buy those little lap desks that are kind of beanbaggy underneath. It's like a flat surface that's on a beanbag and it sits on your lap. Would that work for those of you that are feeling like there's frustration that you can't write?
Well, the chairs are.
Yeah, so that's the other option. That takes not as much space as tables, obviously. We can ask about that, but that's probably more expensive to buy all these chairs. Okay, we will inquire, and hopefully we can get something to resolve quickly. But not all of you raised your hands, so maybe we only need a handful of you. Maybe I'll just order them on Amazon after class. All right. Okay, so I already said a bunch of this, of course not remembering that it's already on a slide. So it's on a slide. Linear systems, why do we use linear systems? First of all, they're super well understood. They've been around for over 150 years. There's a huge, very well understood toolbox for designing linear systems, for analyzing linear systems, for characterizing them, for fitting them to data. And so, in a sense, it's the roots of, it's kind of the foundation for all of engineering to use linear systems, at least as a starting point for designing things. They are an idealization, I already told you this. They don't actually exist, so it's kind of a weird and embarrassing situation where we have this mathematical ideal and we aim for it, knowing that we're not going to actually build something that's linear, and in fact nothing that exists is linear, we're still going to think about that ideal, and because of these great properties that it has, that we can analyze and understand it and reason about it. And so they get used, like I said, in all branches of engineering, in lots of physics, lots of science. There's the quote from George Box. I already told you that. And the point is that linear systems are useful. And I think for me, the key point is really not so much that we believe that a linear model is going to work for describing the brain. It's not. You know in advance it's not. It still provides a way of conceptualizing the problem, of formulating it in its most basic form, and of thinking about what the elements are of the problem. So you find that when you go to build models, especially if they operate in multiple dimensions, really linear systems provide the only sensible tool to start from. It's almost impossible to reason about things in high-dimensional spaces when you're allowing arbitrary functional relationships and interactions. Using a linear, a sort of very simplified linear model, it gives you a starting point. Okay? And then you can get some sort of baseline performance. How well does that work as a model? Where does it fail? Where does it succeed? And then you can try to modify it or enhance it or describe your system. And it often, like it says here, it often gives you a good starting point for more complicated models. Okay, so that's just a little bit of sort of philosophy. And now let's dig in, and we're going to derive, basically all of linear algebra can be derived by starting from this, somewhat scientific perspective of thinking about a linear system or a model of a system that's linear. And let's go through and think about the implications of that. Okay? So imagine I have a system that's linear. That's the L. Okay? L also means loser, as I'm told by my good colleague E.J. Chicholinsky. L is the loser. We think that we invented this. E.J. and I, in 1992, did this to each other and called each other loser, and I think it's spread from there. So we get credit. So here's an input vector V, and it has a bunch of spikes on it. Right? Here's an output vector, whatever, it's not labeled, a bunch of spikes on it. Okay, so this is a system. It takes a vector input, a vector output. Let's just imagine these are finite dimensional and some fixed size. I don't know what that is. It doesn't matter. It's going to be a general statement. There's the input vector. Here's the output vector. Here's the system. And I'm going to assert that the system's linear. If the system is linear, I can do something that I already alluded to when we started describing the dot products and what I call the component selector. Okay? I can take this vector V, which has components V1, V2, V3, V4, down to Vn, whatever it is. Here, let's just imagine 4. And I can rewrite V as a sum, a weighted sum of vectors that have one element at each location. Okay, so here's 4 vectors. Each one of them has a spike plot. Each one of these has only a single element. It's a 1 in a sea of zeros. So this is that component selector I talked about before. We also call these vectors delta functions. We're also going to call these the standard axes, or the standard basis. So there's a bunch of different names that show up in different contexts and in different literatures, and sometimes we'll slip into calling them those things. So these are delta functions. That's a vector with a 1 and all the rest are zeros. They're the standard basis because they represent the standard coordinate system. So this thing, if you were in 2 dimensions, the first one would be a 1 and a 0. That's a vector that has a horizontal component element of 1 and a 0 vertical component, so it's the horizontal coordinate axis. It points in the direction of the horizontal coordinate axis. And then the 0, 1 is the one that points up, right? So these are basically the 2 axis vectors in 2 dimensions. If you're in 3 dimensions, you would add another one, which would be 0, 0, 1, that's coming out of the board, etc. So these are the standard axes of the coordinate system that we're starting with when we represent our vectors. And all you're really saying here is something kind of dumb. You're saying, well, this vector can be written as a sum of vectors, each one lying along one of the axes. Right? So I'm just describing the total vector as a sum of this component multiplied by this axis, this component multiplied by this axis, this component by this axis, this component by this axis. And if I add those up, then I get back the original vector. And it's kind of obvious because, right, multiplying it by this number will just rescale this 1 to make it whatever the appropriate number is, whatever that number is. this one the same, this one the same, this one the same, and when I add them up, these things are going to add up as vectors. Each one will fill in the appropriate component, and they'll have the right height. They'll get back the original vector. So this is basically doing nothing. It's sort of obvious, right? Just describing V in terms of its coordinates. Okay. Now, now that we've taken V and written it that way, we say, oh, well, this system is linear. So the system is linear. That means that the system response to any weighted sum of input vectors is just the same as if I computed the response to each of the input vectors and then took the weighted sum afterward. And I showed you this on the previous slide when I gave you the definition in terms of two vectors. But if you think about it, if it works for two vectors, adding up two vectors, it'll also work for three, because you can kind of add up the first two and use the linearity property, and then add the third one and use the linearity property again. So this actually works for any number of a weighted sum of any number of input vectors. That if the system is linear, it must be that the response of this linear system to this weighted sum of input vectors is a weighted sum. It's a weighted sum. Okay. Oops. It's a weighted sum of the responses to each of these individual ones. Okay. So if I do the little experiment that I already described to you conceptually, I take this linear system and I run this vector into it. This is just an input vector. It has a 1 and all zeros. The 1 is the first element. And I run that through the linear system, and out comes something. Doesn't matter. Now I do another measurement. I run the second impulse in, the second coordinate vector. I run that through the system, and out comes something, whatever it is. I'm being an experimentalist, right? I'm sticking in one thing at a time and making a measurement. Measure the response to this, measure the response to this, measure the response to this, measure the response to this. I get out 4 things, 1, 2, 3, 4. Now, I can say that the response to the original vector is just, the original vector is equal to a weighted sum of these 4 things. So the response will be the weighted sum of the responses to those 4 things. That's using linearity. So I just multiply each of these by the appropriate element of V. V1 times the V1. V1 is the first element of the vector V. It's a number. Multiply it by this vector. V2 times this vector, V3 times this vector, V4 times this vector, and add them up. And that gives me the output. So this thing is linear. So if I tell you that it's linear, it must be the case that sticking this vector in and measuring this output is the same as sticking each of these vectors in, measuring each of their outputs, and then taking a weighted combination of those. It's got to be the same. That's the definition of linearity. Okay. So this is a linear system. It must obey that. And I don't know what happened with my... I'm sorry, the sequence was a little messed up there, but the end result is hopefully clear. Here's a box of input vectors. I told you, we call these impulse vectors, or we can call them axis vectors, or we can call them the standard basis. These are different names for the same thing. It's that collection of vectors which have a 1 in one location and zeros everywhere else, and there's 1 for each component. It's a set of them, in this case 4. These, you can, are a little messed up in terms of the typing, but these things, this box of output vectors, we're going to call the impulse response vectors. These are the responses of this linear system to each of these impulse vectors. So take each of these guys and we measure the response. Those are the impulse responses. Impulse response, impulse response, impulse response, impulse response. So there's a box of these, the blue box. And what we're saying is, since we can do this for any input vector can be decomposed into these guys. And once we've measured the responses to each of these guys, these impulse responses, then we can compute the response of the output. And we can do that for any V, right? In other words, for me to understand what this system does, all I need is this box of vectors, these impulse responses. If you give me this, I can predict what the response will be for any input. And how do I do that? Well, you give me the input V, you give me a V, whatever it is, And what do? You hand me the V, and I go through and I take my box of numbers, and I take the first element of V and I multiply it by this, second element multiplied by this, third element multiplied by this, fourth element multiplied by this, add them up, that's my answer. Now if the system's not linear, my answer might come out wrong, but if it's linear, I know it's going to come out right because it has to obey this superposition property. It has to be, this is an equivalent way to calculate the response. So this is a way to represent, or let's say characterize, a linear system. It's almost an experimental way to think about a linear system, right? If I want to characterize this linear system, what I need to do is make some measurements. That's the experiment. Measure, 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 measure. Put these different things in, 4 different stimuli. Measure the responses. Measure, 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 measure. Hold on to all those measurements. Put them into a table. That's this collection of numbers. This is a table where each row is one of the impulse responses. I collect up that table, and now that I have that table, I'm going to put that aside on my computer in a file, and I can throw away L, the linear system. If I know it's linear, I'm done. I don't need to make any more measurements. I'm done. I can now predict a response to anything just from these. Okay. So that thing, that operation of taking the input V and taking a sum of these things multiplied by the components of V and adding them up, that is matrix multiplication. That's how matrix multiplication arises. And that's, that's basically the core operation of linear algebra.
And one thing to point out is a system takes a vector in and a vector out. They don't have to be the same dimensionality, and in fact, in the example, they work.
And in this picture, they sort of are. Okay. So, actually, before I show you this, let me show you one more thing about this, which is, so the way this works is these numbers are laid out, the impulse responses are laid out here as vectors, spike plots. That's how this is drawn. But this is a box of numbers, and the dimensionality, this is what Mike was just getting at. There are 4 rows in this table because the number of rows in this table was equal to the size of the input vector. I was assuming there were 4 elements in the input vector. And the number of elements in each row is, well, whatever the length of the output vector is. This thing is the length of the output vector, right? So there's a bunch of these, but they all have to have the same length and the size of the output vector. So this is a table of numbers that are arranged such that each row is an impulse response. The way we do this by convention when we do matrix multiplication is the other way around, just to confuse everybody. So the way we think about matrix multiplication is we take those impulse responses and we put them in, we make a table of numbers, and we put the impulse responses in the columns. Okay, so this is going to be a bunch of numbers. It's a vector. And in fact, we usually think of vectors as a column of numbers, so this is very convenient. Now I can just think of each of these as a vector. And what vector is it? It's the impulse response for that particular impulse, the impulse in that position, the first element. The first column will be the impulse response for an impulse in the first entry. This will be the impulse response in the second, third, and fourth. Now, how do I do the calculation that corresponds to computing the output? I take an input vector, that's this. This is V. It has 4 elements. And I have to take a weighted sum of these 4 things, each one weighted by the associated element in V. So I have to take these things, multiply each of them by each of these. This thing times that, this thing times that, this thing times that, this thing times that, and add them up. And so we can write that down. It's always messy to notate these things, but if you want to see what the math looks like, just so you know, it's worth writing it out once at least. And that also lets you think about an alternative way to write it. So let's write it. Okay, so the output, the input is going to be V, the output is going to be, I don't know, W. So W, let's say the kth element of W. Let's write it. Let's redo what's on the slide. colors.
That's what I was thinking.
That's going to get way too fancy, but let's try. What the hell? Let's see what happens. Any more colors?
That should be good and old.
I should. Or until I end up with marker all over my shirt.
And no one can take notes.
No one can take notes. Yes. Okay. So first one is blue, gets multiplied by that. Second one is red, multiplied by that, et cetera, et cetera. Okay, so how do we write that out? Well, this is V, and this is going to be M for matrix, and the output is going to be, I don't know, let's call it W. How big is the output? The input is 4. How big is the output? I didn't actually specify how big the output is. I didn't say how many elements are in each of these columns, right? But whatever it is, it's got to be that many elements. So let's just draw it as something that's the same height.
Yeah,
Right.
previous slide.
It's a vector. The output is a vector. And it has a height, which is the same as that. Okay. And the box of numbers has dimensionality, which is the input dimension along horizontally and the output dimension vertically. And now we can write down what the math is corresponding, or the actual equation that corresponds to this calculation. So this output we're going to call, let's say, W, and we say W sub, let's say the nth element of W is equal to the sum over K equals 1 up to, in this case, 4 of M. So now we have to index and specify row and column, or column and row. And the convention would normally be something like this. Nk, Nk. So what am I doing? I'm looking for the nth element of W. So I come down here to the nth element. What I have to do is take the nth row, the nth element of W, where will that come from? If I'm taking a weighted sum of each of these guys and adding them up to get this, the way that I get this guy, it will come from adding up this guy, and this guy, and this guy, and this guy, the nth row of this matrix. But each of those rescaled by the associated input values. So it's just the product of the nth row of M and each of the elements in that row, K is indexing which column, multiplied by each of the elements in V. All right? So the sum is over the K, the N is specifying which row of the matrix I'm talking about, and I add these up. And you notice that the way I just described this is a little different than the way we originally talked about it. The way we derived it on the previous slide is we said, okay, we measure the response to each impulse. We get these 4 vectors. Here they are, 1, 2, 3, 4. That's our 4 colored vectors. Those are the impulse responses. And then if I want to compute the response to something else, I take a weighted sum of those 4 vectors. But what I just described to you already feels a little different than that. Because what I did is I sort of flipped everything around, and I said, instead of describing the whole process as adding together 4 vectors, let's ask about how we get one element of the output, this element. And if I ask about that one element, where does that come from? That actually just comes from this row of the matrix. So instead of thinking about computing a weighted sum of these columns, which is what's on the left side of this slide, I can also equivalently think about computing each of the elements in the output, which is going to come from a weighted sum along one of these rows. So I take this collection of numbers, there's only 4 of them, and I take a weighted sum of these input values with these 4 numbers. Does that sound somehow familiar? I just took a weighted sum of these with these. It's a dot product. This is just a dot product of one row of this matrix with this input vector v. And on the right side of the slide, what I'm calling the output perspective, is you take this, it's the same box of numbers, but now instead of thinking of them in terms of columns, which is how we derived this, the columns are the impulse responses, we're going to think about it in terms of the rows. And what we're going to do is for each row, we're going to take that row and take a dot product with this input vector v. And that will give us not the whole result, it'll give us one element of the output vector. In this picture, right, I picked an element of the output vector, this one. How do I get that element? I'm not worried about the other ones, just that one. The answer is I take that row of the matrix and I take a dot product with the input. So I can think about this in terms of how I get each element of the output. And the answer is I take a dot product with each row of the matrix. Or I can think about it in terms of how do I get, how do I use each element of the input? And the answer there is each element of the input is getting used to multiply one column of M. Okay, so this blue thing never touches anything else. This first element of V, it only is going to affect, it's going to multiply actually, this column. So if I think about it from the perspective of each element of the input, I think about the columns of the matrix. If I think about it in terms of each element of the output, I have to think about the rows of the matrix. Right? And you can think about it either way, and depending on context and what you're trying to figure out, or what you're trying to lay out when you're designing a matrix or organizing it, you will find it useful to be able to switch back and forth between thinking about the rows versus thinking about the columns. And it's actually really important to be able to think about either one. They are equivalent. It's the same piece of math. This equation corresponds to both of those descriptions. The picture is supposed to sort of force you to organize it one way or the other. You can think about those two pictures. It's the same computation. It's just about what are you focusing on? Are you trying to think about the individual elements in the output, or are you trying to think about what's happening to the elements in the input? Question? Yeah.
Yeah, I think right now it's really abstract. Could you give an example in which you would use like this method, I guess?
Yeah, well, we're going to see that very soon. Soon. I know this is a little abstract, although it's also very concrete, right? This is just adding stuff up, multiplying and adding stuff up. And the reason it feels abstract is because where did this all come from? Usually when you learn this, you go through a bunch of really concrete examples. You say, okay, here's a box of numbers. Here's what matrix multiplication is. You just multiply this stuff like this. And that has the advantage of being kind of a bunch of simple rules or recipes for how you calculate something, but then you're sitting there and thinking, well, why would I do that? And what's the point of doing that calculation? And who made that up anyway? Why did they do it that way? So I'm doing the opposite. I'm trying to show you where does this come from. This emerges from the definition of a linear system. If you tell me that you have a system that's linear, then it is computing a matrix multiplication. This is just a way of us writing down what the computation is. But the abstraction is that if the system is linear, then it must be doing this. And that's also a hook into analyzing and understanding that system from the outside. So if you're thinking, again, like an experimentalist, it gives you something to measure, and it gives you something to compare and to reason about. Okay, we will get to examples of this, and we'll get to a big example, not next week, but the week after, where you'll see lots of this, but not right this minute. Okay, question?
The question there, they should be Vn.
No, this should be Vk. Because this is describing how you compute one output element at the nth output element, okay? And you do that by summing over all the input elements multiplied by the corresponding elements out of that row of the matrix, okay? So the K is indexing the row.
The column.
The column, thank you.
Yeah, that's the main thing.
And this
You
one
say a lot,
is
it's
estimating the
column.
row. Okay, thank you. It's whatever the picture shows. The thing that's varying when you go through this sum is k. So it's 1, 2, 3, 4. That k is indexing 1, 2, 3, and 4. And also over here, 1, 2, 3, and 4. So this is vk, and this is m. K is telling you which column. The row is the same as the row over here, the nth row. Okay? All right, so we're going to try to avoid writing out lots of notation like this, where we express sums over things. But sometimes it's useful just to see it, so that you can see that it's all consistent with this picture. The picture is easier to remember and, frankly, easier to understand, I think. Okay.
Another way I think about it, ever so slightly different, is from the input perspective, the picture on the left. So the input is 4 numbers. You know, what happened at time 1, 2, and 2, 3. Each one of those numbers contributes to the output. And the contribution is sum because it's linear. So I think about that first perspective of that guy multiplying by the first column is, that's what I'm going to give the output. And the next time step has its strength, and that's how much I'm going to give to the output. When we get to shift invariant, that way of thinking about it becomes ever so more clear and important, and that's coming up in a week and a half or so.
Yeah, and the last thing is, and I forgot my prop again. Somehow every year I forget to bring the prop that I need on the second lecture, but I guess I'll just do it in the air. And I probably shouldn't write on the back of the instructions for the TV. Maybe I should.
I know what you're going to write if you do.
I think I will. Here.
I mean, if you want to blank piece of paper, here's a blank piece of paper. Oh, too late.
I'm defacing university property. Okay. So there's our matrix. It's this matrix, okay? And then you have your input vector, which is just these 4 numbers sitting here, right? And so a mnemonic, a way of thinking like physically of what matrix multiplication is you, in terms of dot products, is you tip this over, and then you just feed it through. So it's, you tip it over, and now you say dot product, dot product, dot product, dot product, dot product, dot product, right? Dot product with this, the input, and whatever is in this now column was a row, but now it's a column. Okay. So actually, the right way is to probably think about this. So just take this thing, pull back, tip it over, and now just go tick, 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 tick. And the prop that well, maybe I'll bring it next time. The prop. I left my prop up in my office. How could I do that? Anyway, there's a great analogy to that, which is from a 100-year-old pasta store down the street.
Oh, that.
I'll tell you about it next time. Okay. So you can think about like some sort of conveyor belt where you're chunking through and doing these dot products. 1, 2, 3, 4, 5. Okay. And out of each of those dot products comes a number, and that number is just something that's going into the output vector, right? One element at a time. Tick, 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 tick. Okay. It's sometimes useful to think about that when you're looking at a matrix or trying to understand what a matrix is doing. You kind of have to keep reminding yourself how matrix multiplication works. Okay. So
Fresh pasta next time.
fresh pasta. We'll bring some. I'm going to cook it. Yeah.
So this part makes sense to me, but before when you were saying how the dimensions might change when you compare how it started in the input and that the dimensions might change in the output,
Right.
how would that?
So the dimension. So this thing has a 4-dimensional input. That's the input vector, right? And what about the output? Well, this didn't really specify the output dimension because I just drew these lines.
But it was a.
But over here, you can count it. So it's 1, 2, 3, 4, 5, 6, 7. So in this picture, there are 7 outputs and there are 4 inputs.
Okay,
So the dimensionality of a linear system, the input and output dimensionality do not need to match. They can be anything. They can be 1. You can have an output which is 1-dimensional. Actually, so what happens if the output has dimensionality 1? Maybe it's easiest to look over here. The output dimensionality is the number of rows. If I told you it's 1, then there's just 1 row. And how do you compute the response of that linear system? You just take a dot product of the input with that row. So a dot product, a single dot product, is the simplest example of a linear system. And in fact, all those things that I called operators a few slides ago, those are all linear systems. They're just special cases where there's just one output. Normally, there's a matrix that describes multiple outputs, but you can have one output. That's just a special case. And in fact, that brings me back now. I can fix that notational question. This thing is a vector, and we usually think of vectors as column vectors. We stack up the numbers vertically, and we think of them as columns. If we want to make a row vector, what we have to do is rotate it. And the word for that, when you're thinking about matrices, is transpose. You have to switch the columns and the rows. So we can think of these things as, these are vectors. And they're not, since normally when we say vector, we're going to mean a column vector by convention. We'll think of these as row vectors or transposes of column vectors. And so the way you do a calculation of a dot product in MATLAB is you take two vectors, you transpose the first one, and multiply it by the second one. This is a transposed vector multiplied by the normal vector. And if you have a linear system that has only one output, that's what it is. It's just computing a dot product of this with this. Because there are no other outputs, it's just one output, right? Does that help? Okay. The dimensionality can be anything. It's general. And different systems will handle it differently. Okay. So, right, so this is just to remind you of what that column was, but I already said it, right? This is the response, these are the impulse responses. This first one is just the response to the first axis vector, right? And you're multiplying it by this in order to add it into the output. And this is just a reminder of something I already said also, which is that when you, okay. Now we have to do matrix multiplication. So. I don't know what happened to this sequence. This sequence has gotten really tangled. I am sorry. Okay. So we have to do matrix multiplication. Ignore what's on the slide for a second and let me explain that. Okay. So what happens if I have a linear system? I take an input, I run it into a linear system, and then I take the output, which is a vector, and I stick it into another linear system. So I have two linear systems. I'm going to think about concatenating two linear systems, L1 and L2. First of all, the first observation is, can we make an argument that the whole thing, the concatenated thing, is also linear? Can you see why that might have to be true, or how would you convince yourself that that has to be true? If I tell you each of the constituent systems is linear, why does the combination, the concatenation of the two have to be linear? Any ideas? Do you think it is true? Nobody wants to say. Have I lost you, or are you uninterested, or everybody's just afraid to venture a guess?
You can use the definition of the system.
Yeah, we can just use the definition twice, right? So if I have one, I'm going to go through this one, and then I'm going to go through another one. Right? So I have an input which is, what did I call it? W. And out of this will come, I guess we can call it V. Well, let's put V over here. And in between we'll put Z or something, okay? I'm going to go from W into Z and then into V, right? And I know that this obeys superposition, so if I take two things and I run them, and I add them together and run them through this one, what I'll get out is the same as if I had put them through individually. And that's also true for this guy. Then I have to convince myself that that would be true for the whole thing. And it should be reasonably clear. I think I don't have to write it all out, because basically, maybe I do need to write it all out just so that there's no doubt. So if I tell you that L1 applied to W1 plus L2 applied to W2 is equal to L1 applied to W1 plus W2. I'm leaving out the scale factors A and B. We're just going to do adding. Okay. So that's because L1 is linear.
What is L2?
Sorry, that's L1 still. Thank you. And now what I want to do is I want to apply L2 to this. So I'm going to take L2 and apply it outside of this, right? It's getting messy notationally, but conceptually that's what I'm saying, right? So I know that L1 is linear, so this inner thing was equal to this. Now I'm going to apply L2 to that, to the outside of those two things were already equal, so if I apply L2 to them, then I must get the same answer. So L2 applied to this has to be equal to L2 applied to that. And then the last step is, oh, wait a second, L2 was also linear. So L2 applied to a sum of two things. Doesn't matter that they came out of L1, whatever they are, it's just two things. L2 applied to a sum of two things is the same as L2 applied to each of those things individually and added up at the end, right? L2 times L1 of W2. Okay. And we're done, because what we just did is we said that L2, that the combined system of L2 applied on top of L1 obeys superposition. If I apply L2 on top of L1 to a sum of inputs, W1 and W2, that's the same as applying L2 on top of L1 to the first input and L2 on top of L1 to the second input and adding them afterward. Okay? We just proved it. That probably, for those of you that are not used to writing out math, this probably doesn't help very much. It looks like a lot of notation, like more than was necessary to express something very simple, which is, if I put these two things through the first system and they obey superposition, like I could have put them through separately and measured, or I could put them through together as a sum, and I get the same answer. It will, and this is also true for the second system, then it'll be true the whole way through. I could put one thing the whole way through, and I could put the other thing the whole way through, and the output of each of those added together is the same as if I had put them together in the beginning. Okay. So concatenations, the short version of that is a concatenated combination of linear systems is a linear system. And that means, since this whole thing is linear, there must be some way to express this whole thing as a matrix, right? But it was also true that each one of these could be expressed as a matrix. So what's the relationship between the matrix for this one, the matrix for this one, and the matrix for the whole thing? There must be some way to express that. And the answer is, the answer is the definition of matrix multiplication, multiplying a matrix by a matrix. The way you combine two matrices, applying one and then the other, is you can multiply the two matrices together to get a single matrix. And how do you do that? You just think through what you know the matrix is doing. So a matrix is, so let's take one of the matrices, right? And it is, let's call this M1. So that's the matrix for L1. Okay? And what it's going to do is give you a weighted sum of these columns. You can think about each of the columns going through. What's the second matrix going to do? So you have to apply the second matrix. This is already going to get a little bit strange. So let's make it a different shape. Let's make this one square, for example. And we're going to write it here. So the first thing is, why did I write M1 here and M2 here? It's like backwards. The systems are going in the other direction. L1 happens first, and then L2 happens. But I just wrote the matrices the other way. The answer is because the input's over here in this matrix picture, and these matrices are being applied to this input, and the first one that gets applied is M1. And then, on top of that, you're going to apply M2. So that is the correct order. We write it, it's sort of backwards from the way we would draw it usually when you draw a system diagram by convention. You draw it left to right, the way we read and write in English, from the left side to the right side. But the way matrices get stacked is the other way around, by convention. Okay. How do we think about what the combined matrix should be? because here's two individual matrices, but really there's a single matrix that describes the whole thing because the whole thing is linear. And the answer is, well, trace through what happens to the elements, right? This element, what happens to this? It's going to multiply this column, right? And then what happens to that? That then becomes the input to the next system. This column is a vector. So this matrix operating on this vector is just matrix multiplication again. I take this matrix and I multiply it by this vector, right? And which means, think of it as each of the rows of this matrix is going to do a dot product with that vector. What about the next element? So I'll do that one in blue. Here's the next element. It's going to multiply this column. And what am I going to do with that column? If I just had that column as an input to the next system, I would take dot products again of that column with each of these rows. So the way and what comes out in the end is the result of taking this column and taking its dot product with all of these. So the combined matrix, call it M3 if you like, that represents the concatenated operation of M1 followed by M2, can be computed by literally taking this matrix and applying it to each of the columns of M1. Treating each of those columns like a vector, which it is. It's what are those vectors? Those are the responses to an impulse, right, in the first system. Take each of the impulse responses of the first system and run them through the second system to compute the impulse responses of that system to those impulse responses, and then you get the concatenated impulse response. In other words, all we're really doing is saying, if I put something into the first element, it puts out this, and then the second thing puts out its response to that. That's the impulse response of the combined system. So all we have to do is calculate the impulse responses of the combined system, and we do that by applying this system to the impulse responses of the first system. Okay? So that sounds very complicated, but it's actually pretty simple. This is just a rule for combining matrices. Take two matrices, turn them into one. The way you do it is just apply this one to each of the columns of that one. And as you do that, each column you're going to get out a vector, and you're going to stack those together in a new matrix, which is going to represent the impulse responses. Each of those will be the impulse response of the combined thing. Okay? So that's what matrix multiplication is. It's defined by what you would expect to happen if you concatenated two linear systems. All right. Question?
I'm trying to wrap my head a little bit around the dimensionality
Yeah.
of the vectors here. So
Yeah.
is it possible to apply M2 directly to the input vector there, or do they need to share a dimension?
Okay, so the answer to your question's on the slide. And what you are recognizing correctly is that in order for me to apply this to the output of that, it must be that the output of this is of suitable dimensionality to serve as an input to this, right? So where are the input and output dimensionalities represented in a matrix? The input dimensionality is the width of the matrix. It's the number of columns. The output dimensionality is the number of rows. And so what you're saying is the number of, let's see, rows of this matrix, that's actually the first system that gets applied, has to be equal to the number of columns of the second matrix. So the way it's drawn here, there's three colors here, red, purple, and cyan. The purple is showing up twice because those things have to be the same. This dimension, the height of this matrix, must be equal to the width of this matrix. The other two, the red and the cyan, can be anything. So you have an arbitrary input dimension, that's red, and you have an output dimension for the first linear system, and that has to match the input dimension for the second linear system, and then that linear system can have whatever output dimension it has. It can be, again, arbitrary. And the end result, when you combine these two matrices, is, well, it has to be able to take an input, which is the size of the red thing, and have an output, which is the size of the cyan thing, so it must be red by cyan. Okay? So it has a height, which is the height of this second matrix, or first, if you're going from left to right, and it has a width, which is the width of the first matrix, or second if you're going left to right. Okay? This is the one that gets applied first, the one on the right, right? The order is swapped. M1 goes here, M2 goes there. Okay, but the dimensionalities have to match up. When you multiply two matrices, just like if you multiply a matrix times a vector, the dimensionalities have to make sense. And the same thing is true if you're multiplying a matrix by a matrix. Yeah, question?
Could you please use notations to represent those dimensionalities?
Do we use notation to represent the dimensionalities? Usually we
Numbers,
don't
color
specify that when we write down the matrices. If you want to get mathy, there are ways to do that. If you want, I can write that, but I don't know if it's going to help.
It's not help.
It's
The
gonna
color
help.
bars is confusing.
Pardon me?
The color bars are pretty confusing.
Color bars are confusing. This is confusing?
Yeah.
Okay,
All I can say is I'm gonna go over this again next time.
We can go over it tomorrow too.
Yeah,
Yeah.
let's, and we're out of time anyway. So let's leave it at that for now. I'm going to put notes, linear algebra notes online. It's a PDF. It's about a 10-page document that kind of goes in very terse and direct way through all of these things, so you can see them written out. And we'll also figure out the video thing to get decent quality video up online, because the video thing seems to be not working. Okay, thanks.